Hello everyone, welcome to this lecture series on probability and statistics, and this is lecture number 3. In this lecture, I would just like to recap whatever we have done, give a brief description of everything that we have covered so far, and wanted to go more in detail into sample spaces and sigma fields. And in this lecture, my primary focus will be on examples to understand different type of sample spaces, different type of sigma fields. And in the end, I've also included a homework question, which I will discuss in the next lecture. And yeah, hope you guys enjoyed the lecture. So let's do the recap first. So, we have covered these important topics as of now, and I would like to just re-mention what they mean so that we are on the same page. So, the first topic is random experiment, and random experiment is any experiment in which a particular instance has unknown outcomes, but there are a known set of possibilities. So you know that there is a certain set, and any time you do that experiment, you will get you will get something from that set only. There is a known set of possibilities, but what you will get at that particular instance, you do not know. A very simple example of a random experiment is tossing a coin. You know you will either get a head or a tail, but say you toss a coin right now, you don't know if you will get a head or you will get a tail, but you know for sure that you will get either of the two. So yeah, so that takes us to the second concept, which is a sample space. And what is the sample space? Sample space is all possible outcomes of the random experiment. So these known set of possibilities which I'm talking about, the set, if you make a set of all these known set of possibilities, that is our sample space. And a sample space can be finite, it can be infinite but countable, and it can be infinite but uncountable. So there are different sample spaces that are possible, and yeah, we'll try to study all different types of sample spaces in this lecture. So yeah, just keep listening on. What is an event? An event is any subset of the sample space, and this is the part which we are interested in. When we come to probabilities, we define the probability of an event. We don't define probability of the whole sample space. We don't define probability of just each element of the sample space, or just like there are very interesting things that can come out, and that are actually subsets of the sample space only. Those are the things which we are interested in. Those are the things in which those are the probabilities we are interested in. Hence, we have a term for it, which is an event. And as I have defined, that sample spaces can be of different kinds. It can be finite, infinite, countable, uncountable. And because of that, you cannot define probability in all subsets of the sample space. That's the issue. Uh, if we only have finite or countable sample spaces, as you can see here, in that case, it's not that difficult. Any subset of the sample space, you can define a probability. But if the sample space is uncountable, right, there are a lot of weird subsets that can come up in which, first of all, maybe we are not interested at all. Even if we are, it's not so easy to define a probability on it. Hence, to simplify our life, we have come to sigma fields, and sigma field is actually restricts us to the collection of the subsets of the sample space, and only those subsets of the space for which we are interested in defining probabilities, and also in which it is actually possible to define probabilities. So hence, uh, if the sample space is finite or countable, In that case, sigma field is the set of all subsets of S. There's no issue on that. You can define a probability in any subset of S if it is finite or countable. But if it is not, if it is uncountable, in that case, it is usually open closed intervals on the sample space. So for the most practical purposes, we will deal with interval sample spaces, and these are the uncountable sample spaces, and generally closed open intervals of that, like subsets of these, are where probabilities are defined and where the sigma field is defined. Like that's how the sigma field is defined for these sample spaces. And we're going to only focus on those subsets, not some random weird subsets. That is what sigma field actually does. It gives us more structure in case our sample space is, like even for very simple experiments, the sample space, it can be uncountable. So it was important to define a sigma field for that purpose. Next, we'll go through 4 examples, each covering each type of sample spaces, and we'll also discuss what the corresponding sigma field will be. Sigma field, you can just think of sigma field as the set of subsets. It is actually the collection of subsets of the sample space where we are interested in defining the probability, where we will eventually define probability. We will not define probability in any other subset which is not relevant and which is not part of the sigma field. So let's go. This is the most simple example. We have been talking about this a lot. So let's revisit this again. Okay, a coin is tossed once. What is the sample space? So the sample space is head, tail. It is the set of all possible outcomes. We know all possible outcomes is head and tail. And what about twice? Twice would be you either get 2 heads, you either get 2 tails. You first get a tail, then get a head. You first get a head and then get a tail. These two are different events. They are not the same. You can't say that getting head once and getting tail once. Yes, they are both once, but what comes first? Order is important. Order is important because if you don't look at the order, then the probabilities you define will be wrong. And we will revisit this and I will explain you why, if you don't consider these as two different uh, cases, how the probability will get wrong. So now both of these sample spaces are finite. So what is my sigma field? It is actually all subsets. There is no doubt here. All subsets. And although this one would be difficult, if you consider this one, right, we can actually write down the sigma field. It will be the empty set, head, this is one subset, this is the other subset, and this is the set itself is always a subset, and null set is also a subset. And this also satisfied the rules of sigma field, that is the empty set being part of the sigma field closed under complementation. Closed under complementation means that if I have H, then the complement of H, which is T, should also be there. T is there. If I have T, the complement of T, which is H, that is also there. If I have HT, the complement of HT, which is phi, which is the null set, is there. If I have phi, the complement of the null set is, which is the full sample space, is there. And the union, if I have two subsets, then the union of those should also be there. So the union of H and T, which is HT, is there. The union of HT and phi is HT, that is there. So this satisfies all rules of sigma field, and really there is no question of doubt here. This is just a finite set, and you can consider all possible subsets in this case. You don't have to think a lot here, right? One thing I want to mention here is that the set of all possible subsets of a set is actually called a power set. And if your set has, say, n elements, then your power set has 2 raised to the power n elements. Why this is true, I will talk about in combinations, permutation and combination class, which I will take further. But for now, you can take my word for this. So for this example that we saw, the number of elements in the set is 2. So the power set is will have 2 raised to power 2, which is 4 elements. And that is what we have here. Okay, great. Now suppose a die is rolled n times. So suppose n is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each of these 10 blanks can take numbers from 1 to 6, right? 1 to 6. So what is the sample space? Now I can't list down each and every element here, but we can mention it in a smart way. So my sample space is x1, x2, x3 till x10, where xi belongs to 1, 2, 3, 4, 5, 6, right? I is from 1 to 10. So it's saying that all possible tuples, and the number of elements in this tuple is 10. All possible tuples where x1 to x10 is between 1 to 6. Make a set of those. That is my sample space. And the number of elements, this again involves permutation and combination principles, but the number of elements that are there in this sample space. Now each of these uh, blanks can have 6 outcomes. So we have 6 into 6 into 6 till 10 in this case. So 6 to the power 10 elements are actually there in our sample space we're talking about here. And again, however big this number is, it is finite. It is not an infinite case. And again, all possible subsets will be our sigma field. We can define probability on all possible subsets. We are not going to restrict ourselves here. For finite sample spaces, it doesn't matter. Okay, now coming to a different type of experiment. A coin is tossed until a first head appears. So let's talk about the sample space here. Now, it's possible that you get head in the first try. So that is one possibility. You can't deny. It's not the case that you will never get. It's rare, and it's based on luck, but you can get it. And the other case would be to get tails and then head, or you get 2 tails and then you get your head, or you get 3 tails and then you get your head, and so on. This is infinite now. I don't know when to stop. It is possible that I get like 1 lakh tails and then I get a head. Very unlikely, but possible. So I can't stop. Like, it would be wrong to stop anywhere because you're not listing out all the possible cases in that case. So this is an infinite set, but it is countable. The thumb rule to determine if it's countable is that you can step by step count the elements. So 1, 2, 3, 4, like that, and you can keep counting it. So this is an infinite and countable set. And here again, although I cannot again list out all possible outcome, all possible subsets of this, but for all practical purposes, for defining probabilities, any subset of this, may it be finite, may it be infinite, we can define probabilities on that, right? There's no restriction again here. It's not that we will get some weird set where we cannot define probabilities. So here as well, all possible subsets is our sigma field. Now let's go to our last example. You have a circle, the radius of this circle is r, you have a pointer and you rotate this pointer. Okay. And now I tell you what is the sample space? Like where will you land? What is the sample space of the different of you landing somewhere? Now I cannot list this in numbers. I can't say 0, 1, 2 or something like that, right? I can come somewhere in between. It's just like a circle. I can get anywhere between 0 to 2 pi r. 2 pi r being circumference of the circle. Okay. It can be anything, right? I can land here, I can land here, I can land here. I cannot I cannot stepwise give numbers that okay, I can land over here, over here, over here only. Right. It's a free pointer, it can go anywhere. So now this sample space is uncountable. It's infinite. And here, not all the subsets of this can have a probability. It's only open and closed intervals are possible. So you can define a probability on 0 to pi r, say. You can define it from 0 to pi r. You can define it from 0 to 1. You can define it from like this. So all these places, all these events, probabilities can be defined. And that is our sigma field. That is our events of interest in these type of cases. Now, I want to give you a homework problem. This is a bit difficult, uh, but we'll discuss it in the next lecture. So you can just try it on your end. Uh, let's get into it. So we have a table which is divided into lines, and the distance between the lines is 2l, and you have a rod of length l, and you just throw it here. Okay, you just throw the rod. What is the sample space in this experiment? And by the sample space, I mean what are the different positions in which the rod can land, uh, and find a way to determine to, to uniquely tell the position of this rod in this table. That is just that's the problem. We'll discuss it in the next class. First thing we'll discuss this only. So yeah, just think about it. And just to let you guys know, this all the questions discussed here is from the book Rohatgi and Saleh, Probability and Stats. If you intro to probability and stats, if you are interested, you can. I'm loosely following this book, so you can keep this. You can keep referring to this if you have any issues. And yeah, that's all for this lecture. I hope you guys enjoyed it. Please let me know any feedback because I've just started this channel. Uh, yeah, and I want to make statistics intuitive, and want people to understand it in a way that I did. I really enjoyed it in when I was studying it. So that's why I've created this channel. Uh, please support and please let me know how you like this lecture. Let's meet next time. Thank you. Bye.